Let me open briefly in a prayer. Dear Lord, thank you again for bringing us all here safely. Thank you for the warm weather and the nice evening we have together. Thank you for letting attendance not drop off too much. Thank you for all the wonderful people here. Please bless our time together and please help everyone to get home safely. In Jesus' name we pray, amen. Quick announcement, I think some of you got an email from Pastor Cleve today that was signed by me. Usually I don't sign my emails Dr. Pacini, so it's okay to call me Ross, just in case that email came through. But just so you know, if you reply to that email, it won't come to me. So I'll have my email address at the end. If there's any questions that come up or anything like that, just shoot me an email anytime. And that invitation's always open. So if there's things that come up and you have additional questions about some of this, feel free to reach out anytime. Catch me after class, catch me at church, anything like that. So thank you all for coming again. This is, I think, our fourth session so far. Quick reminder, and I'll remind you again at the end, I'm not here next week, but please still come. There are two very good videos that we're going to show from Answers in Genesis, one from Ken Ham, who we saw before, and one is a very good video on a creationist who goes to a campus and confronts evolutionists. It's very, very interesting. They cover a lot of the things that we talked about here. And Dave and Randy have kindly agreed to help me with that. So we're going to test out the AV at the end to make sure everything works out okay that way. Yeah, yeah, there'll be a little less of that. Very good. So just as in review for anybody who's missed a session or anything, and again, I'm going to kind of emphasize the same thing every time. Why are we doing this? Why do we have this discussion? Well, again, these are the literal first words of the Bible. And so if we don't believe the literal first words of the Bible, how do we believe anything else in the Bible? And that's why I consider this topic so important and why it's such a passion to me. The key to secularism that we see in our society today, again, has its foundations in evolution, right? We don't need God, we don't need a creator. Science did it all, therefore there really is no reason for morality. And over the last couple of weeks, we've discussed at quite great length some of the fundamentals of evolution, how those genetic mutations occur, and then we talked about why that theory is so flawed. So if you recall the number of missing links, incredible gaps that we see in the quote-unquote evolutionary history, both in animals and in humans, and hopefully in plants too, because that question's come up. The concept of irreducible complexity, that some systems are so complex that you cannot evolve them one gene at a time. You cannot develop an immune system or a coagulation cascade that requires multiple interacting parts. You can't develop that one protein at a time. We talked very specifically about harmful mutations. In fact, most mutations are harmful. And we talked about why a quote-unquote beneficial mutation is so hard to come by, and why the idea of going from a simple bacteria to a complex man really is in contradistinction to what science shows us. And then finally, we talked about my favorite argument, which is the disadvantage of us humans, that we actually are very evolutionarily poor because we are very slow to pass on our genetics. We're very fragile compared to things like bacteria. So before I move on, does anybody have any residual outstanding questions about that? Perfect. All right. So it's clear. So now hit me up if you have other questions. So recall the goals for the course. We talked about the fundamentals, why the theory is so flawed. So tonight and 2 weeks from now, we're going to discuss the problems with the Big Bang Theory. And that's going to be most of tonight. Most of 2 weeks from now are all the evidences for a young Earth. I will caution you that tonight's is probably my second most complex topic, so bear with me and please forgive me if it gets a little in the weeds. I also, even though I have degrees in biochemistry and microbiology, I do not have them in astronomy and physics, so don't hit me too hard on the questions here. But so why does the age of the Earth matter? Well, we've talked about many times, for evolutionists, time heals all wounds, right? So we talked about numerous flaws in evolution. The universal answer that I get all of the time for this is, like I told you, Ross, it just took a lot of time. So I hope I've proven to you that time is a woefully incomplete way to solve all the problems of evolution. But does the idea of an old Earth even make sense? Was creation actually spread out over billions of years? And as a quick side note, like we've talked about before, and we will summarize in the end, and like Ken Ham points out, this is not necessarily a salvation issue, right? You can believe in an old earth and still be saved by Christ. What we're trying to get at here is the fundamentals. So this is not a salvation issue, but it is sort of a fundamental biblical issue. So remember, and this is the most important thing, without billions of years, evolution absolutely falls apart. The last 3 weeks were a complete waste of my breath if the earth is young. If we know the earth is young, it doesn't matter any other argument we've given for evolution, it completely destroys it. But this is why secularists and evolutionists get even more defensive about the age of the earth than they actually do about evolution. They'll more readily argue with me about evolution. We can have a good discussion about that. They'll just tell me I'm crazy about the age of the earth because they know if they lose that argument, they've lost all arguments. So briefly, we're going to go back to a little high school chemistry. I know you're excited. But all matter is made of chemicals, and those chemicals are composed of elements. There are 92 naturally occurring elements on Earth. We have discovered others and been able to create others, but there are only 92 naturally occurring. Each of these elements is made of a subatomic particle of protons, neutrons, and electrons. Stop me if this sounds fascinatingly reminiscent of high school. Protons are large, positively charged particles that exist in the nucleus. Neutrons are equally large, but have no charge. And electrons are really, really tiny, negatively charged pieces of matter that float around the nucleus. Protons and neutrons are about 2,000 times the size of electrons. So does this picture look familiar? Everybody's seen the atom before. This is what we're talking about. We're talking about elements. So the center here, the nucleus, is made of protons and neutrons. And then very rapidly, these electrons fly around here. And so what they're showing you in the ellipsis is just how these electrons fly around. If the nucleus were a size of a tennis ball, the atom itself would be the size of Memorial Stadium. So all of the mass, even all the weight of an atom is this tiny tennis ball, right? And then the length that these electrons are flying around, they're up in the nosebleeds, where the only place where you can get tickets now. Well, actually, it might be easier now. But tennis ball to Memorial Stadium is how we make the atom. Now, I'm sure this brings back lots of memories and fun nightmares for people, but this is the periodic table of elements that tells you about the elements and things you've likely heard of. Potassium, that starts with a K, because helium, oxygen, lead, iron, uranium, gold, etc. Uranium being the heaviest of the naturally occurring elements. So these elements all combine to form all of the things we see in matter. And you've probably heard of H2O, water, CO2 or carbon dioxide, C6H12O6 or glucose, or for some, the favorite C2H5OH, alcohol. All life is organic, meaning it's based on this element right here, on carbon. So all the things that we see in naturally occurring life are carbon-based forms. So with that basic background in chemistry, let me turn to the Big Bang Theory. So throughout most of history, until the 1800s, the Earth was felt to be around 6,000 years old. Well, how did we arrive at that number? Well, it was based in no small part on the accounts of Genesis and things that we've talked about. Genesis very clearly gives us the genealogies of the Bible, and if you add up all those numbers, you come up roughly to about 4,000 years until Christ, and we know there's been 2,000 or so years since Christ. And the fossils and rock layers were felt to have been laid down as part of Noah's flood. We're going to return to that extensively several weeks from now. In the 1800s, however, geologists began to have the idea that rock layers were laid down slowly over a long period of time. And this led to the theory that the Earth was hundreds of millions of years old. Then came along radiometric dating in 1903 and throughout the 20th century, and the age of the Earth was changed from hundreds of millions to now billions of years old. To 4.5 billion is the latest thing we are told that science knows the Earth is. We will explore radiometric dating in painstaking detail a few weeks from now. So the Big Bang Theory itself, well, this theory developed in the 1900s and actually was in large part due to a physicist who conveniently happened to also be a priest. and wanted to explain the origin of the universe. And based on this theory, the universe is now believed or known by the scientific community to be 13.8 billion years old. The long and the short of the Big Bang Theory is this. What they have observed is that the universe is constantly expanding. We see it getting bigger and bigger and bigger. So, if we assume that we back up in time, it gets smaller and smaller and smaller and smaller and smaller and smaller until you get to a single point, which they call the singularity, and from this single point, boom, all matter expanded. So we see everything expanding right now, and we're still seeing it expand, so we assume that if we back up, it comes to a very, very small point. All that currently exists, according to the Big Bang Theory, was compressed into this so-called cosmic egg, which was about the size of an electron. Remember, we talked about the size of the electron, right? Tennis ball, Memorial Stadium. That electron is somewhere in Memorial Stadium as a tiny little speck. Everything in the universe was in that tiny little speck in that cosmic egg, because science. Eventually, this egg exploded due to some sort of instability. And first, this was a very rapid expansion of this egg. And then there was an actual explosion, followed by cooling, and all of this occurred in incredible fractions of a second. This process then formed those subatomic particles, and by subatomic particles I mean the three things we talked about: protons, neutrons, electrons. And they eventually found each other, came together, and formed hydrogen, which is our simplest, smallest element, and helium, which is our second simplest, smallest element. So you with me so far? Big explosion, subatomic particles, now we've got hydrogen and helium. So then these gases, hydrogen and helium, start diffusing outward in an ever-expanding environment that we know as space. So these gases start expanding out. The subatomic particles came together as hydrogen and helium. Now they're expanding out. And eventually, these gases then came together, and they came together as stars and galaxies. Inside these stars, these gases, under huge amounts of heat and pressure, fuse together to form the other 90 elements we see on the periodic table. So, big explosion, small particles, hydrogen, helium, they come together, they start banging into each other and forming heavier elements. Eventually, these stars with heavier elements explode. And these heavier elements, potassium, sodium, xenon, uranium, they get integrated into future stars, which we call second and third generation stars. So we've got explosions, subatomic particles, gases come together, form a star. Stars form heavier elements, they explode, and form new stars. Got it? Okay. Our sun is a third generation star. So a star explodes, elements together. Star explodes, elements together. Boom, there's our sun. The Earth and all of its inhabitants are made up of some of this residual stardust that created the various elements needed for life on Earth. So we've all got stars in our eyes. Our solar system formed about 5 billion years ago, with life starting about 4 billion years ago. Multicellular organisms, meaning more than bacteria, originating about 1 billion years ago. Modern man emerges about 40,000 years ago. So let's dig a little deeper into the Big Bang. So I went to the most important source I can, which is Wikipedia. But trust me, if you want to know the secular, very left opinion, you go to Wikipedia. So this is how they describe it. Between 0 and 10 to the negative 43. Does everybody know how exponents work? That's 1 over 10 with 43 zeros. It's a really, really, really small fraction of a second. Electromagnetic forces, strong, and they break these four. They say there are 4 forces that came together. Basically, this cosmic egg was energy. Okay, and this is how they explain it. Cosmic egg was basically energy, and we know from Einstein that E equals mc squared, you can convert energy to mass. I won't go into all the details of that because it'll make your eyes explode. But suffice it to say that current physics theory is that energy and mass are somewhat convertible. So they break this down into 4 forces that existed. These electromagnetic forces, what they call strong nuclear forces, weak nuclear forces, and gravitational forces. These were all unified as one. And the universe was about 1.6 times 10 to the negative 35 meters in size. That's really, really small. And 10 with 32 zeros behind it degrees Celsius. That's really, really hot. Between 10 to the negative 43 and 10 to the negative 37, the temperatures fell rapidly, and the gravitational forces separate. Between 10 to the negative 37 and 10 to the negative 32, something called inflation occurs, which we'll come back to later. The universe drops its temperature by a factor of 100,000, and by this time, in these fractions of seconds, the universe has expanded 10 with 78 zeros behind it times in size. Then it cools for a long period of time until we get to 10 to the negative 2. So again, we're still in very, very, very small fractions of a second here. The electromagnetic forces now and the weak nuclear forces, they all separate. So the 4 forces, if you will, now separate. At 10 to the negative seconds, that's when we get our protons and neutrons. And then at about 1 second, we get our electrons. And at a few minutes into the Big Bang, we get hydrogen and helium. Got it? Ready for the test? Okay, at 379,000 years, we get something called cosmic radiation. So, let's talk about some problems. Any questions about that before I... I don't know. You'll have to check with the Wikipedia people. To that point, let's start with some obvious flaws. Really? That's probably my biggest question. Really? Everything in the universe was once compressed to the size of an electron? Honestly, that takes more faith than believing in God does. So where did all this material come from? We've got everything on the earth. Where exactly did it actually come from? Do you want to believe in eternal God, or do you want to believe in eternal matter? What's an easier concept? What makes more sense? What's written on your heart? So what in the world caused the explosion of this cosmic egg? So ultimately, as you can probably guess, the Big Bang Theory is really more of a creative story, couching itself as quote-unquote science, especially the Wikipedia explanation telling us what happened in the first nanoseconds of life. They have no evidence to back that up. That is complete conjecture. It's completely made up. But let's talk about some more specific problems with the Big Bang Theory. We've all seen magnets, right? And we all know that magnets have 2 poles. You put the 2 poles together and they push each other apart. You put opposite poles together, they stick together. Magnets have a north pole and a south pole, so they'll stick together. There's something in there called monopoles, which are theoretical molecules that only have 1 pole. They're only a north pole, they're only a south pole, they're very stable. Through mechanisms I'm not going to get into, the Big Bang Theory should have produced an abundance of these. So much so, these should be the main constituent of the universe, yet we can't find a single one. Then there's something called the flatness problem. Basically, the expansion of the universe had to be incredibly finely tuned to gravitational forces. We're all familiar with gravity, right? If I drop this, Dave would be mad at me because it would break. But any variance of these gravitational forces would lead to a universe so tight and dense that it would actually fold on itself and collapse, or not dense enough and it would all fly rapidly apart and doesn't work. The current universe is very, very close to this critical density point, and so the original universe had to be even closer to keep it intact. A variant of 1 times 10 to the 62nd power. Okay, that's a very large number, or a very small number if you want to look at it that way, would have thrown it all off. The odds of this happening are obviously extremely dismal. These 2 problems are well known by secularists and Big Bang theorists. And so they have developed a theory called inflation that I told you we would come back to. And that's that time mentioned right before the universe expanded to this huge amount, that factor of 1 times 10 to the 78th in a fraction of a second. Right before that was this thing called inflation. And I didn't bother to put a whole thing together on inflation, but suffice it to say the issue is there's absolutely no evidence for it. It's complete conjecture, and it's starting with your conclusion and working your way backwards. Well, we know the Big Bang Theory happened, we know the monopole problem, we know the flatness problem, so here you go, inflation. And on top of that, there are actually multiple different theories of inflation, and even the so-called scientists can't agree on the correct one. So again, their approach is, we know it happened, let's just invent a story. This is basically a theme we see in both evolutionary gaps and Big Bang gaps. Then there's something called antimatter. Side note, because it makes me laugh. My dad told me as a kid, matter and antimatter cannot exist in the same place at the same time. So he thought my brothers were matter and antimatter because they could not get along in the same room and be at the same place. So that's why every time I hear antimatter, that's what I think of are my brothers. I'm not sure which one was antimatter and which one was matter. But the theory that the universe basically, again, we talked about this, started as energy. And that energy was converted to make matter, like hydrogen and helium. Well, the problem is when you convert energy to matter, you create equal parts matter and antimatter. Antimatter is the exact opposite of what we are, of matter. So here, the proton, in the antimatter world, the protons are negatively charged. The electrons are positively charged. Everything is a mirror image. And if we did convert this energy into matter through the Big Bang, we should have equal parts matter and antimatter. But we don't. There's virtually no antimatter. Let's look at the star problem. Recall from the theory the original stars had hydrogen, helium, and trace amounts of lithium, which is the third element, the third heaviest. So hydrogen's the lightest, helium's the next, and then lithium. And we only got these heavier elements when these stars exploded and formed other elements, which were then taken up by subsequent second and third generation stars, like our sun. So some of these first generation stars should still be around, but they aren't. All known stars contain heavier elements than they should for first generation stars. We can't find any evidence of these so-called first generation stars that the scientists tell us everything came from. Let's look at something else. I like to call this Big Bang and evolving theory. So, in the 1980s, the rate of expansion was felt or known to be 50 kilometers per second per megaparsec. What's a megaparsec? That's 3.26 million light years. I'll come back to that concept a little later. But suffice it to say, this is very, very rapid expansion. And in the 1980s, we knew that's how fast the universe was expanding. In the 1990s, they said, no, that was wrong. It's actually faster. It's 80 kilometers per second per megaparsec. Thus, in the 1980s, it was known the universe was 16 to 18 billion years old. In fact, I remember as a kid being told that, and I suspect many of you in the 80s were told that. It's 16 to 18 billion years. But now, those guys were idiots. We know the universe is 13.71 billion years old. And the inflation portion of the Big Bang wasn't actually part of the model until 1984. It got added when people pointed out the flaws that I mentioned. The model of 1984 didn't include modern cosmology, things like dark matter and string theory. These have all since been incorporated into the Big Bang. So remember that scientists in 1980s felt just as confident, cocky, and arrogant about their numbers and models as scientists do today. Yet the models of the 80s were absurdly wrong and very different by today's standards. They can't both be right, but they would both tell you you're idiots. The theories evolved so much, and this is a theme I've mentioned over and over and I'm going to mention over and over, that it's become non-falsifiable. That's a key word to remember, non-falsifiable. There's nothing that can disprove it to the scientific community. You should always test your own theories. Well, what could prove me wrong? If there's nothing that could prove you wrong, that's not science anymore, that's religion. And there's a place for religion, but let's admit when something is religion and not pretend that science is something it's not. So they'll simply adapt a model based on new evidence, but the fundamental idea that we know a Big Bang took place, we know the Big Bang took place, that always will be in their head. And again, that's no longer science. At that point, it's religion. So if we want to have a religious argument, happy to do that. But let's not call this science anymore. Now, ironically, as I've already kind of alluded to, the scientists in the 1980s and the early Big Bang and the modern ones would both quickly tell me and the people who believe in young Earth that that's merely faith. Yet, interestingly, the biblical model for creation, unlike the Big Bang Theory, hasn't changed. 6 days has always been 6 days. The ages of Adam, Noah, Abraham, these are all well-documented, well-known, and unchanging information. So it's ultimately a matter of faith to buy into many of the propositions of the Big Bang, and I would argue that believing in God is less of a lift and far easier than it is to believe in the Big Bang. One final point. Actually, somebody made this point. I forgot who it was in something I was reading, but actually the Big Bang is somewhat useful for creationists and those of us who come from a biblical perspective. Ultimately, this is science conceding the universe had a beginning, i.e. at some point it was created. And the mere existence of something created is essentially an acknowledgement for a creator. Furthermore, the characteristics of the Big Bang, what they've described in there, require such precision and timing and intricacies that they could ultimately only occur through an intelligent creator. So in some ways, the Big Bang Theory itself is actually an homage to accepting God. Questions before I change topics here? Correct. Correct. Yes, that's another issue. Yeah. We're still on the hunt. Yeah, correct. It changes. I think that's fair. Yeah. Well, that's a good question. I mean, that's the ultimate question, right? Where did we come from? So, yeah. Good. Yes, fire away. Yeah. I don't know. That's a good point. Yeah, and everything else. Yeah, actually, the Creation Museum has a great planetarium show that they do, talking about how many stars and sort of the vastness of the universe and whatnot. Absolutely. Okay, so I'm going to turn, speaking of that, I'm going to turn to the universe and stars and light years. So, basic astronomy, which I was really bad at as a kid and probably still am. Light waves travel at about 300 million meters per second, or in easier to understand terms, 671 million miles per hour, which is what my wife tells me I drive. The amount of distance that light can travel in a year is called a light year. So a light year, even though it has the word year in it, is a measure of distance. It is not a measure of time. It's how far can light go in a year, which is 5.8 trillion miles. So a long way to go. The kids are really asking, when are we going to get there? So what this means is light that is produced from something 1 light year away from us will be seen by us 1 year later. So there, if it's a light year away, they'll see that green light a year from now if they're a light year away. For example, our sun is 92 million miles from us. That's 8.33 light minutes, meaning the light we see was created 8 1/3 minutes before we see it. Does that all make sense? So because objects in the universe are so far away, so astronomically far away, we measure their distance in light years. The universe itself appears to be billions of light years across, to Dave's point, with how many stars there are. So how do we measure these distances? And this, I did this a lot the other night practicing myself, and you can do this at home. It's a fun game. But we can use basic trigonometry to determine the distance of close stars by using what's called a parallax. Okay? So take your finger and point at something, okay? Anything in the room. Close one eye and see what you're pointing at, and close the other eye and see what you're pointing at. You see that that changes? Now, move your finger closer to your eye and do the same thing, and the distance changes even more. But if you move it farther away, the distance changes less. So you can play with that at home. You won't look crazy at all. Now, we can measure the distance between your eyes, some are wider than others, and the angle between that and what your finger points to with your right eye and your left, and we can generate a triangle from this. That triangle allows us to calculate the distance your finger is away from your eye. So you're looking at a background object and you're looking at the point here and point here, measure this, make a triangle, do lots of fancy math, and you can come up with something. So this is demonstrating it here. So these are your two eyes. This is your object, this is your finger, I'm sorry, and this is the background that you're comparing to. So if you pointed to a light with one eye, you see it at this blue point. With the other eye, you see it at this red point. And this is called a parallax. This same principle can be used to measure a near star using a background of much farther stars that don't appear to move because they are so far away. And conveniently, the Earth has two eyes. We rotate around the sun. So in the springtime, we're at this angle, and then in the fall, we're at this angle. So what we do is we look at how this star looks compared to this background. This background is the thing you were pointing to, the things that don't move, and we see how the star looks in the spring, and then we compare to how the star looks in the fall. Make sense? And we can use that because we know, just like measuring the distance in your eyes, we know how far we are from the sun here. So we can create this trigonometric, another subject I was terrible at, triangle here, and we can measure this angle. We all know there are 360 degrees in a circle. Each degree can be divided into minutes and then into seconds. So there are 3,600 arc seconds in each degree, 60 seconds per minute. Excuse me. So if the angle of difference for a star measured 6 months apart was 1 arc second, the object is said to be 1 parsec away. You may recall I used the term parsec earlier. A parsec is a measure of distance. It is 3.26 light years. So we know, don't worry about the math here, but we know that if this angle here is 1 arc second, that translates to this object is 3.26 light years away. Don't worry too much about the math, but suffice it to say, we can look at this here on Earth, we can look at it in December on Earth. We know we can calculate this angle because we know this, and we know this, and that will tell us how many light years away something is. This is actually a very, very accurate way. It's been well validated to tell how far something is away. Now, all stars out there are farther from the Earth than a parsec, meaning their angle in arc seconds is very, very small. So because of that, we can only measure objects about 20 parsec away, or 65 light years. So the stars that we can measure by this method are all very, very close to us. They're all 65 light years away. Now, we've launched some satellites, and we increased that measurement to 600 light years for something called the Hipparcos satellite in 1989. And then Gaia was launched in 2013, and now we can get pretty accurate measurement out to 10,000s of light years in 2013. And another word, I had to write down the pronunciation so I could pronounce this. Now, that's the most direct measurement, is parallaxes. Okay. Now, we're going to talk about a bunch of very complex indirect measurements just to give you an idea of what goes into this. But the Cepheid variables is an indirect measurement. So try to bear with me on this, but we can measure a star's brightness to determine its distance. We compare a star's apparent magnitude, meaning how bright do we see it here on Earth, and compare it to something called the absolute magnitude. Well, how do we determine the absolute magnitude? The absolute magnitude is what we know, or how bright a star would be if it was 10 of those parsecs away. Okay? So we use those measurements to compare what we see versus what we know it would be if it was closer. So there's something called a Cepheid variable, which is a pulsating star with a temperature that's very similar to our sun. And these stars, they pulsate and increase and decrease in size and temperature, and we can actually measure how long these cycles take. And we know from our sun, that the length of these cycles is directly proportional to that star's absolute magnitude. So that's how we know its absolute magnitude. So once we know that, we compare the apparent magnitude, in other words, how bright do we see it, to the absolute magnitude, which is what would it be if it was 10 parsecs away, and then we can use that fancy formula to determine how far away the star is. Now, there's something else called the Crab Nebula, and this is actually a really interesting story, but Chinese astronomers observed this huge exploding star in 1054, and it's actually well documented in literature. And modern photographs that have been taken of this thing, decades apart, actually show it to be expanding. And knowing this rate of expansion, and knowing we know exactly when it exploded in 1054, we combine this with what's called Doppler information. Doppler is when something is headed towards you, it looks a little different or sounds a little different versus when it's headed away from you. Ever hear that train go by? Same thing. That was fascinating, I'm sure. Same thing exists in light. We have slight color changes when stuff is coming towards you versus going away from you. So we know the rate of expansion of when this thing, and we can determine this Crab Nebula is about 6,000 light years away. Well, interestingly, this nebula also contains something called pulsars, which can be picked up kind of like radio waves. And knowing how far away that Crab Nebula is, we've been able to determine other distances by studying the frequency of other pulsars. So we can apply this information and determine that distance. So these sort of indirect measurements have allowed us to determine the size of the Milky Way galaxy to be roughly 100,000 light years across. But what about the extragalactic distances? What about the really far differences? So we have a couple ways to do this. There's something called the classic novae, which are eruptions on white dwarf stars caused by an interaction with a nearby star. And these things seem to have a predictable absolute brightness. So if we see one of these in another galaxy, we can use that previously discussed apparent magnitude versus absolute magnitude to calculate the distance. There's something called supergiant stars in similar galaxies that also tend to have predictable and stable absolute magnitudes and brightnesses. And then galaxies like the Milky Way contain these globular clusters of stars, and the largest ones tend to have the same diameters, so their apparent size can be compared to the absolute size to estimate how far away they are. Something interesting is called a Type 1a supernova for really people into this. So what this is, you've got a two-star system called the binary system, and it's a disintegration of one of these white dwarf system that produces a Type 1a supernova. And all of these Type 1a supernovas are so similar that they produce essentially the same absolute brightness. Now, these are very rare events, but with the right high-powered telescope, which I'm sure the Branch Oak Observatory has, you can see these in other galaxies and estimate the distances to those galaxies up to 10 billion light years away. Finally, redshift. I mentioned the Doppler phenomenon. So remember, the universe is expanding, and when an object moves away from us, the visible spectrum of light is pushed towards the red end, so it looks more red to us. And the farther away something is, the more red it will be. So we can use the amount of redshift, if you will, to determine that distance. So an object moving away from us will look more red to us, an object moving toward us will look more blue to us. So, let me just pause here for just a sec to contemplate the size of the universe. In many ways, the size and complexity of the universe ought to cause us to pause and marvel at the power and wisdom of our Creator. When we look at these distances and we look at the amazing structure that is the universe and how small and insignificant we are, it should cause us to pause and thank God for our existence. In the same way that things like the human brain work are unfathomable and complex, so too is the universe in its size and complexity. Again, all of these things should actually point us to God, not to random chance. So, I want to go over in the last portion here the quote-unquote light year problem, because the light year is often used as a way to tell us that this is how we know the universe is old. Before I do that, do you have any questions on how these measurements occur? Okay, yeah, you got them all ready for the test? Yes, sir. Mm-hmm. Totally fair point. It's the best they have. So I wouldn't say that it's in any way perfect. I think the only thing that we can really reliably, at least on the, and again, I'm not an expert in this, Dave, you probably know more far about this than I do, but I think the parallax is a pretty legitimate way of doing it, and all the rest of these are specifically called indirect measurements because they're not absolutely known. So that is a fair point, and we are going to address that a little bit here. So, okay. Mm-hmm. Yeah, yeah, it is. Mm-hmm. 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 Yeah, no, that's fair. Yeah. Yeah, yeah, no, absolutely. So let's talk about the light year problem. So given these amazing distances, isn't this proof that the Earth is that the universe is actually billions of years old? How could the stars be created on day 4 and light be visible to Adam by day 6 if these things are billions of light years away? I will couch this with this, that ultimately we do not know the answers to some of these questions, but I'm going to walk you through several theories. So theory 1, we just mismeasured. So everything I just went over with you is complete garbage and we're just wrong. I don't think this is the best counter argument. I wouldn't suggest this one, but I throw it out there. These are pretty reproducible and based on observation rather than many of the evolutionary and cosmologic theories we've already talked about, which are based on conjecture. So I think it's still possible. I think we should always be open to that we have completely mismeasured. But more importantly, the reason I probably wouldn't use this argument is I actually think the vastness of the universe is an incredible argument for God and His majesty. So I wouldn't really jump to, well, we're just mismeasured. So theory 2, and this one's pretty common, well, God created the light paths. And this is kind of what I always grew up with, well, God just put the light path there, and it's been used by creationists for many years, and it certainly has some merit. The theory is that God just simply created the light path. So not only did He create the star, but He created the path itself. Well, the problem with that comes in what we observe. And we've already discussed that we've seen what are called supernovas. Remember that type 1a supernova, an exploding star? And given that those stars are millions of light years away, and if we said the Earth was only 6,000 years old, that would mean that star never existed. And it was rather that God painted an image in the sky. And basically, many of the stars we see we're simply watching a movie, not the reflection of real stars, but we're watching a movie. To me, and I think to the author I read on this theory would imply that God is deceiving us a little bit. I think it's still possible, and it may very well be the explanation, but it does beg the question a little bit, is God deceiving us and creating an illusion rather than what He said He created? He said He created the stars, and He said He created actual stars. He didn't say He created a movie or something for us to watch. This doesn't seem super consistent with the nature of God, but I think we do have to entertain that is a possibility. Theory 3 is something called the speed of light decay. And the theory here is the speed of light was actually faster in the past, and has been decaying over time. So in the past, the speed of light was much, much faster than it is now. Well, there's a couple of problems. Unlike some of the evolutionists, we actually will admit when we can't see something in real life, and we haven't seen a decay problem. But the bigger problem is that many constants in the universe depend on the speed of light, E equals mc squared. And if we change the speed of light, many, many other aspects of physics change with it and would really undermine a lot of things that we've looked at in general. However, having said that, even some secularists are actually re-looking at this, and they actually do have some ongoing work in this area for other reasons. So Theory 4 and Theory 5 are probably my favorite, but Theory 4 is a relativity model. This is based on Einstein's theory of relativity, and ultimately, it boils down to the idea that time passes differently in different places and different scenarios. So something that takes seconds on Earth is actually years in the stars. As an object approaches the speed of light, its time is actually slowed down, and this is something called time dilatation. Gravity also affects the passage of time. Interestingly, a clock at sea level ticks slightly slower than on a mountain. Now, it's a very, very small difference, but this can actually be measured with atomic clocks. So there does seem to be some difference to the passage of time based on areas where things are. And this has led somewhat to the anisotropic synchrony convention theory, say that fast, that light is basically traveling in no time because of relativity. Now, I'm not an expert on relativity, but I thought this analogy was decent. It's not perfect, but decent. So, picture this as a plane leaving New York City at 2 p.m. It lands in Denver at 2 p.m. The flight actually took 2 hours if you were on the plane, but it arrived and left at the same time at 2 p.m. So from the passenger perspective, from you on the plane as light, you were up there for 2 hours. But from the perspective of the person in Denver, the plane arrived at 2 p.m., even though it left at 2 p.m. technically. Not a perfect analogy, but these are the theories of relativity that light experiences things differently when traveling at the speed of light. And then finally, Theory 5 is something called the Dasha theory. Now, I actually like this one a lot. Now, I will admit this is not the most scientific explanation, but this is probably my favorite. So, Dasha is a Hebrew word that basically means sprout, and originally used in Genesis 1:11 when vegetation was formed. So, vegetation had to sprout, grow, produce very quickly on day 3, so that animals on day 5 and 6 would have something to eat. In other words, the days of creation were a little different than what we observe today, right? We don't put a seed in the ground and it's ready to eat in 2 days. But something was different about the creation week. God made the creation week special and different. And by the same token, stars created on day 4 had to be visible by man on day 6. So the theory is that God simply sped up certain processes during a very miraculous creation week. And certainly much of creation week, we know, required processes outside our modern scientific processes. So the rules that govern the world today may be very different in physics than they were during the creation week. Is it a perfect explanation? No. Is it completely scientific? No. But I think it fits pretty well with what the Bible describes in general. Now, creationists aren't the only ones with a light year problem, and this is important to remind the secularists. So I like to say we're not alone. The Big Bang Theory also has some serious light year problems. So based on the knowledge, science knows, again, I always use the term knows loosely, but science knows that the universe has an extremely uniform temperature of 2.7 Kelvin. For those of you who aren't familiar with the Kelvin scale, it basically is the Celsius scale minus 273 degrees. So 0 Kelvin is something you've probably heard of, absolute zero. It's when all matter would absolutely freeze and not move at all. So that's negative 455 degrees. You get that deep, deep freeze. For that to happen, for there to be a uniform temperature across space, bodies in space have to exchange energy and heat. Think of it this way. You put an ice cube in a cup of hot coffee. They are going to exchange heat, and eventually become the same temperature, right? So the universe is the same way. They have to exchange heat in order to keep the temperature constant. Well, while you've got the Big Bang, A and B, let's just use points A and B. These are very far apart. And the fastest way to exchange heat energy is going to be with light. However, points A and point B are so far apart that they can't have exchanged light and energy in 14 billion years. These are the maximum distances that light could have traveled for A and B to be exchanging heat and for the temperature to become so uniform. So they also, in secularism and Big Bang theory, have problems with light years, which is why they are exploring some of those explanations that I already talked to you about. So this is not necessarily just unique to creationism. And this problem, by the way, is called the horizon problem. And scientists fix this problem by adding inflation. Well, again, we talked about inflation. It's complete conjecture, and it amounts to religion. So once again, they're accepting the Big Bang as fact, and then just inventing solutions when problems arise. And this really puts them in a weaker position than those of us that at least have the biblical history to back up our religion. So what if we can't solve the time travel problem? Remember that our understanding of these things is constantly changing, and things we quote-unquote know today to be true will be proven absolutely false in the future. Light is incredibly, incredibly complex, and we don't fully understand it. It actually acts as both a particle and a wave. It has mass, it has energy. It is something that I don't think anybody fully understands, and it still holds many mysteries. And I don't think we should get so hung up on one single mystery when there's a wealth of evidence in the cosmos and elsewhere that points to a young Earth, but that's next week's topic, and by next week I mean 2 weeks. So, in conclusion, the Big Bang Theory is a complex theory that attempts to explain the origin of the universe. But as we've seen, it's a theory full of holes that is degenerated to one of simply faith. The universe, if you take home one thing, is a fascinating and expansive creation that should really leave us in awe of God's genius. However, the vastness of the universe is not a guarantee of its old age. So next couple weeks, reminder once again, I'm out of town. We're going to show 2 videos, In 6 Days by Ken Ham, and Evolution versus God, which is creationists who interviews evolutionists on campus. It's really enjoyable. And then in 2 weeks, we're going to talk about one of my favorite topics, which is the arguments for a young Earth. Science constantly tells us it knows the Earth to be billions of years old, but there's actually a wealth of science that points to a much younger Earth, and those are the things that we're going to cover in 2 weeks. And these arguments are a little simpler to understand than all the complexities of what I went over tonight, and these can be really useful for talking with your secular acquaintances, so I hope you'll join me for that. And that's all I have to say about that. But that, again, is my actual email, so please don't reply to the fake email. What questions can I answer, if anything? Yeah. Through different media, yes, but in space it has a constant speed because space is essentially all the same. Mm-hmm. Well, you're right? Nobody knows. I mean, only God knows that, and you're exactly right. There's no way to test that, and yes, that would be another potential explanation, is there's things beyond our understanding, for sure. I think that's fair. Good. Yes, sir. Mm-hmm. 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 Correct. Yeah. No, I mean, you're right. I mean, all these things are points well taken, that there are a lot of things we don't understand. So I don't think it's fair for either side to say, well, we know this. And it goes to your earlier point of how did we get this, absolute magnitude. A lot of this is conjecture. So, but I want you all to at least understand where the conjecture comes from scientific. But yeah, your point is well taken. Yes, sir. Yeah, no, that's right, and that was actually something that I was taught in my college physics class too, which it was their way of kind of explaining relativity was exactly that. You get down to really, really short time and then infinity, which never made sense to me, but yes, I think that's part of the theory of relativity. Yes, sir. With Forrest Gump? Oh. Mm. Yeah, that's actually a very good question. So the Answers in Genesis book does actually have a chapter on that. Admittedly, I didn't read it, but I will tell you what little I know is that we don't know, right? I mean, God didn't speak specifically to did He create other life forms somewhere else. Do I personally think He did? No. Do I think it's possible? Sure. And do I think it would change my religion in any way if there were life forms out there? No, it wouldn't. I would assume that they have the same God and they, worship Him on a different planet, and that's how it goes. So I think that's a fair question. There are some better, longer explanations from AIG than I can give you, but yeah, I mean, I think that's a legitimate question. And I know people on both sides, both pretty religious people that think that aliens definitely are out there, and pretty religious people that think they're not out there. So I don't have a strong opinion, but that's a good question for which I don't have a perfect answer. Well, yeah, that's true. I mean, that's yeah. Mm-hmm. Yeah. No, that's true. That's a good point. It does depend. He's the president now. Just kidding. Just kidding. Just kidding. Yeah. Sorry. All right. No, 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 no. You're the only hand I see. Mhm. 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 Yeah, no, and that's the point I was trying to make is that I think the scientific the accepting by the scientific community of the Big Bang is in some ways the acceptance of a creator, because something existed, something was created. It was not just it always has been. It's something started. So something that starts has to have a creator. And yes, so in some ways scientists have backed themselves into a corner and sort of admitting that yes, there is a creator. So I think that's a fair point. Hmm. Yeah, they're Husker fans. Yeah. Hmm. Hmm. Yeah. I think so. So in theory, you've got something pushing. It's almost like there's waves that are being pushed, And when you push them, it makes it appear more blue. When you pull them or hold them back, it makes it appear more red. It's just like that train engine that goes past you. The sound becomes higher frequency, lower frequency. Yeah, yeah. Give me a second. Yeah. Mm. Mm-hmm. Yeah, because it's infrared. Mm-hmm. Mm-hmm. Not that pretty, huh? You're ruining it for us. Gotcha. No, that's a good point. Fair enough. Fair enough. Good. Anything else I can address for anybody? Yes, sir. Mm-hmm. Yeah. No, that's a good point. That's a fair point. So, well, perfect. Well, as you may recall, bonus for the people up front. Randy, remind me how many tables we need in the back. Is it 7? 6. Not 5, not 7, because we had that problem last week. Mm-hmm. Yeah. So if we could just get a little help rearranging tables and chairs with those in the back. I'm around for a little while because I got to figure out some AV stuff. So if anybody else has any other questions, let me know. Remember, video next week, and there are 2 videos, and then we'll talk about the young Earth in 2 weeks. Thanks, everybody, for coming. I appreciate it. Yeah.